This is a topic on flux, field and field intensity. And why I'm taking all these things together, there is a reason for it. And let me explain this to you, or let me state it at the very outset that flux is the most basic electrostatic physical quantity. And why do I say that? It is the most basic electrostatic physical quantity, even more basic than field, even more basic than force. There are some reasons to it which we'll discuss in this particular explanation. Now, a lot of complex equations like these and a lot of complex diagrams like these have been used to explain flux, and we will come to that after some time. But for now, we are going to try to simplify this thing and to explain flux as it really is, as nature intended it to be. So, how do we understand flux? In order to understand flux, we have to start with an analogy. Let's consider a bulb, a lightning bulb, and you are observing the bulb. We can very easily say that there is some power associated with a bulb. Every bulb has a power. Let's say this particular bulb here has a power of 10 watts. 10 watts. And this bulb releases light in all directions. And the light being released is isotropic in nature. What is isotropic? It is equal in all directions. You go at some distance from the bulb and try to observe distance. You observe the bulb at this distance. And then you observe the bulb at this distance. And then you observe the bulb at this distance. What is exactly happening? If you are observing the bulb from a close point, let's say here, you will see that the brightness is high, and if you observe the bulb from this distance, you will see that the brightness is low. And why is that? There is something called as intensity that you might have studied in waves, and intensity is simply power per unit area. So the power of the bulb is obviously 10 watts, and since the bulb is isotropic, it is emitting equally in all directions. The area that we are going to consider is the spherical area, because all directions are same, so the area is going to be 4 pi r squared. Now this r squared is what we call as the inverse square law. Inverse square law. And it would be interesting to tell you at this point of time that you have studied inverse square law in all basic forces. For example, in gravitational force, the inverse square law was g m1 m2 upon r squared. And in Coulomb's law, the electrostatic force was k q1 q2 upon r squared. So there is something special about this r squared that we need to understand, and then we will get to know the basics of flux. I believe this is a question running into your heads right now. What the hell is happening and what I am talking about? How come a light bulb can even compare to the inverse square law? I mean, what is the connection there? And why am I doing this? Sounds like utter stupidity to me. Comparing a light bulb with inverse square law that deals with gravity and electrostatic forces. But let me tell you, it is what it is. Both these things are very similar in these situations, and that is why I have taken this analogy. So coming back to the analogy, instead of a light bulb now, let me take a charge. I'm going to take a point charge. So here is my point charge. And we like to call this point charge something. So I'll say that, okay, this point charge is plus Q. And what's so special about this point charge? This point charge is emitting something. Now that is a very important word, something, because that something is going to play a full role in understanding of what flux is. So it is emitting something. Question marks, we don't know what that thing is, but yes, it is emitting something. And just like the light bulb, it is emitting that particular something in all directions equally. So again, it is isotropic in nature. Whatever is being emitted is isotropic in nature. More importantly, whatever is being emitted is just like the power of this light bulb. Do you remember? The power of this light bulb was 10 watts. Now I'm not saying that this charge is emitting power, that would be stupid to say, but it is emitting something that is just like power. And the most important part of that being just like power is that its value is fixed. Whatever that something is, its value is fixed. It is not changing with respect to time, it's not changing with respect to distance. The value of that something, the value of this something is fixed. Now, as that something starts to distribute in its surrounding space, first it is here, and then it moves out, and then it moves out further, and then it moves out even further more. And as it starts to distribute itself in the surrounding space, we see that the something is fixed. We cannot change that. Let's say there are 10 quantities of something, and those 10 quantities are being distributed in space. So as they move further away in space, the intensity decreases. I'd write the word here, intensity. Now what is this intensity going to be? That intensity is going to be something, this is a funny word here, something divided by area, and since it is isotropic in nature, the area is going to be 4 pi r squared. So the intensity is going to be something divided by 4 pi r squared. And what do we call that something? We call that something as flux. So what I'm trying to say here, I'll summarize this again. This charge, just like the lightning bulb, emits something that we call as flux. And this flux is fixed. This flux is not changing. This flux is totally, absolutely fixed. As the flux gets distributed, it moves out in the surrounding space. And the word is isotropically. I'm sorry, I haven't written that word. I need to write that word. The word is isotropically. Very important word. So as that something moves out in space isotropically, equally in all directions, its intensity decreases. And what is intensity? That we learned from the last page. That was something. Now I should replace this something with flux now. So that intensity is going to be flux upon 4 pi r squared, because this flux, this something, is being distributed equally in all directions. So let's take our charge once again. This is our charge. Its magnitude is plus q, and as I said it before, it is a point charge. Now it is emitting, as I told you, it is emitting something. That something is what we call as flux. We are not going into whether it is a scalar quantity, vector quantity, or whatever. We are simply saying that it is emitting something in all directions equally, and that is called as flux. But as it moves ahead into space, it is being spread equally in all directions. So you might notice that the intensity decreases. The intensity decreases as we move from closer points to farther points. The intensity diminishes out. That is what we are trying to state. Now, what is that something? That something is flux, that we are going to represent as phi, and that something is q by epsilon naught. And when it is being spread into space, so let's say it is being spread at a certain point P, what is the value of the intensity of flux? Let me write this word, intensity of flux. The intensity of flux is going to be phi upon 4 pi r squared. And why is that? Simply because it is being emitted isotropically. So we'll have intensity of flux as q upon epsilon naught divided by 4 pi r squared. Now if you look at it closer and you bring the epsilon naught down, you will have q upon 4 pi epsilon naught r squared. And what that is? We know that this is what we call as field. Field due to a point charge. This is the field due to a point charge. So let's rewind it again. What we have learned so far. This point charge emits something in the surrounding space, and that is what we call as flux. Flux is phi equals to q by epsilon naught. Now as that flux gets distributed around, it travels farther and farther in the vacuum or space nearby. It diminishes in intensity. Why does it diminish in intensity? It's very simple thing. It takes more and more space around it. So at a certain point, let's say at this point P, if this distance is r, and if we draw a sphere surrounding that charge, we draw not a very good sphere, but will may do. Okay, at this point P, if we draw a sphere, the overall flux, the total flux on this entire sphere, I want you to take note of this, the total flux on this entire sphere is going to be q upon epsilon naught, but it has distributed into a larger area. So the intensity of flux, and now we will name it as everybody else names it. We will call this at field intensity. Everyone was asking me what is the difference between field and field intensity. They are the same thing, and field represents an intensity. What intensity or which intensity does it represent? It represents the intensity of flux. So q upon epsilon naught upon intensity is always 4 pi r squared, and that gives us q upon 4 pi r epsilon naught r squared. So you get the field intensity at this point P. Now if you keep a charge at the point P, if you keep a charge here at point P, and let's say you keep a charge small q at the point P, the charge q will experience a force. And what will be the force? The force is small charge q into the field intensity. So that is going to be let's call this charge as q dash. So q dash into E. So q dash into the field intensity, that is q upon 4 pi epsilon naught r squared. So now you understand what is the sequence of things. First, a charge creates flux in the surrounding space. As that flux spreads in the surrounding space, its intensity decreases because of this inverse square law, and the intensity, as we move farther away and farther away from the charge, it will decrease. Now if you bring another charge q dash in the vicinity of that intensity, it will experience a force, and that force is going to be q dash e, that is q dash into electric field intensity. Now we want to understand some properties of the flux, and we want to guess whether flux is a scalar quantity or a vector quantity. We know that field for sure is a vector quantity, but we want to know what flux is. We only know that flux is something that a charge emits. Now consider this spherical surface here. You can see it's not circular, it's spherical, all directions. Now this charge q emits a flux of q by epsilon naught. Now the question is the flux emitted dependent on the nature of surface? Is it? I mean, let me reframe this question. I have the same charge and I take a very absurd kind of a surface here. What is the flux passing through this surface? And what is the flux passing through this surface? Now, if any charge emits q by epsilon naught, irrespective of anything which is a constant quantity, which is a fixed quantity as I told you, the flux through this surface or the flux through this surface are both going to be equal, and they are going to be q by epsilon naught. So if flux is independent of the nature of surface, it's independent of the direction of surface, it's independent of anything whatsoever, we say that flux is an absolute scalar quantity. And there are more things to it, but for now we will take flux as scalar quantity. Flux is a scalar quantity. Okay, let me put this in a different perspective. Let's say I have a surface here, and this is a charge, obviously. This is a charge q. And what do I do is I put a dent on the surface here, let's say. And when I put a dent on the surface, this kind of a dent on the surface. Now again the same question, does the flux change? And the answer is no, because the flux that is being emitted by the charge is always q by epsilon naught. So no matter what kind of closed surface you take, what kind of denty surface or smooth spherical surface you take, it is always going to be q by epsilon naught. So now we come to a very basic problem, and that problem is how to find flux mathematically. Now I have given you some hints prior to that. We know that flux was q by epsilon naught, and we know that electric field intensity was basically q by epsilon naught upon 4 pi r squared. That we could say that flux upon 4 pi r squared, or we could say that flux upon area. So if you could multiply field with area, we could get flux. But it is not as simple as it sounds. I mean, it's not a straightforward multiplication of field into area, and I'll explain this to you why. Now I'll write again what I said in the last page. I would say that we could find out flux by multiplying field with area. But I've told you before that it is not that simple. And let me tell you why it is not that simple. Let's consider this field here. Let's consider this field here. These are the fields of this point charge. Now, it's very simple. You multiply this field. I mean, it's very easy right now. It's very simple. The field at a certain distance r at point P is going to be uh, q upon 4 pi epsilon naught r square, where r is the distance obviously, and then in order to find flux you simply multiply it by q upon 4 pi epsilon naught r square into 4 pi r square, that is the area, and you get q by epsilon naught, that is the flux. Okay, so it looks simple that way. But let's say again I will make this surface denty. Let's say I have a denty surface here. I beat up this sphere and form a dent here. And now I want to take up the field lines, or I want to understand the field lines here. I have taken the same sphere. Let me all draw it with a solid line. I have taken the same sphere, and then I have beaten up at this point. I have beaten the sphere up at this point to create a dent like this. Some dent like this. It might be some kind of a. Now you can see that the surface area has changed. The surface area has changed. This surface area is very different from the past area that we were discussing. The past area was simply 4 pi r squared. That was the area of the sphere, 4 pi r squared. Now you cannot multiply this new area and get the flux. And why is that? Because the flux is same. The flux of yellow lines, let me remind you, the flux of yellow lines, the flux of this charge coming out of this area, no matter how denty you make it, is always going to be q by epsilon naught. But if you take this denty area and you multiply this field, if you multiply this yellow field with this denty area, with this area here, you will get to know that okay, this area has changed. Now this area is not 4 pi r squared, and if we multiply field with area, if we take a different area than this one, if we take a different area, we will get a different value here, right or not? And if we get a different value here, we are doing something wrong, fundamentally wrong, because the flux is always going to be q by epsilon naught. So this is clear that we cannot directly multiply field with area. I mean, that is something wrong there. I mean, we have to check out what is wrong there, but we cannot multiply field with any area, because if you multiply field with this denty area here, this area is going to change and your flux is going to change, and that is wrong because flux is constant. So what do we do? So we'll see that in a different page. So now we take up the same charge again. This was your charge Q. We know that this charge Q has field lines in all directions. And we take that denty area, this denty area. And field lines are passing through this denty area. We cannot take this denty area as we have discussed before. If we take the denty area, if we take the area that is deformed, we'll have a different area and we'll have a different flux. We can't afford that. Flux would be wrong. So what is the mathematical implication here? And how do we solve it? So what do we say? We say that we are not talking about area. We are talking about area vector. What is this thing here? Area vector, something new that we came across. So area vector is basically a vector. Let's say if this area is ds, there will be a vector perpendicular to it, and it has the same magnitude as the area, and its direction is perpendicular to the surface of the area, and that is what we call as an area vector. For example, the screen in which you are looking at has an area vector that is coming out of the screen towards you, and that is what we call as an area vector. So if we are talking about an area here, the perpendicular to it might be like this. Let's say this is your ds, so that will be your area vector ds. And if we take an area vector here, the perpendicular to it will be something like this. Let's say something like this, and that will be your new area vector ds dash, because this area is ds dash. So we are not talking about in terms of area right now, we are talking in terms of area vector. Okay. I have a field like this, and this here is the area. Now you can see that the area vector is perpendicular to the area. All the green lines represent the area vector and all the yellow lines represent the field. Now we cannot directly multiply field with area in order to find flux. The flux is not simply equals to field into area. What is it exactly equals to? It is equals to the dot product of field and area vector. Now what the hell is this? The dot product of field and area vector will give us E into A into cos theta, and I have to mention here what is cos theta. So this angle is going to be theta. So instead of drawing hundreds of lines, let me show you in just one line here. If this is your field and this is your area, so this becomes your area vector, and this is the angle between them is theta. The flux of this field is simply going to be equals to E into A into cos theta. Now what is A into cos theta here? A into cos theta is going to be, if you can understand the angles, this angle is theta here, so this angle here is also going to be theta. So if you can understand the angles here, and this is area vector A, so it will have a component that is in the direction of field, and that is equals to A cos theta. And we are not multiplying field with any area, we are multiplying field with the area vector that is in the direction of field. Field with area vector in the direction of field. Let me show this to you again. In case of sphere, it was very easy. There was no doubt about it. This was your charge. The field was absolutely straight. The area vector was absolutely straight. And the area vector was parallel to the field. So you could simply say that flux is equals to field into area vector. Flux. But now if you have a strained surface like this, and in that strained surface you have a charge. For that charge you have a field like this, let's say here, and the area vector is like this. Let's consider this a small area. Area vector is like this, so this small area would be called as ds, let's say. So this is area vector ds, and this is your field, and the angle between them is theta. So we are considering only that part of the area vector that is parallel to the field. So the flux is going to be E into ds, E dot ds, or that is going to be E ds cos theta. Or that we can simply say that that ds cos theta is the component of area vector that is parallel to the field. Let me draw the components of the area vector. It will have a parallel component and a perpendicular component. So we are talking about the area vector, this area vector that is parallel to the field, the white line. We will call this as ds parallel and we will call this as ds perpendicular. And that is what we are doing here. So in order to find flux, you need to find out, or you need to multiply field with the area vector that is parallel to the field. And then we can keep on doing it for all area vectors. We have this area vector here. Field direction would be something like this, right? And the area vector would be something like this, ds dash. Likewise, we can have a field direction here and area vector is something like this, so ds dash or ds double dash, and we have to do it for the entire surface, or let's say a part of the surface. So we can say that the flux will be equals to the integration of E dot ds. Now we are not discussing right now whether the area is closed or open. I'm not going into those things. The area can be open, the area can be closed. All I'm saying is that even if there is an open area like this and there is a charge like this and there is a field here and you have a ds vector like this, you will have to integrate it for the entire area, and that is why you are using an integration sign.